Variations on a theme, and today we're going to look at some problems that use the random function, or that require the use of the random function, and can be solved with an approach called rejection sampling. Here we look at two problems that are listed in LeetCode. One is problem 470, implement rand 10 using rand 7. Given a function rand7, which generates a uniform random integer in the range of 1 to 7, write a function rand10, which generates a uniform random integer in the range 1 to 10. So that means we basically have to adjust our range in which we generate numbers and make sure that we still get like the same uniform sampling. And specifically not make use of any standard functions that would give you math random straight out of the box. So here are a couple of examples. If you draw 1, you might get a 7. If you draw 2, you might get an 8, which is beyond the 7, and a 4. Draw 3, you might get something like 8, 1, and 10 uniformly distributed over the range from 1 to 10. Rand7 is predefined as one node, and each test case has one argument, n, the number of times that rand10 is called. And the second problem is called generate random point in a circle. 478, flagged as medium. Given the radius and x, y positions of the center of a circle, write a function rand point, which generates a uniform random point in the circle. Note, input and output values are in floating point. Radius and xy position of the center of the circle is passed into the class constructor. A point on the circumference of the circle is considered to be in the circle. Run point returns a size 2 array containing x position and y position of the random point in that order. So first we have the x position, then we have the y position. Let's have a look. Solution rand point is called. And so we get like output is 1, 0, 0, and then 3 empty. Oh, like, sorry, so that's still the input. 1, 0, 0 being a point on the circumference. And then we get like 3 empty points. And then the output would be null, and then we would see 3 points sampled on the circumference of that circle. So that's that. The second one has a solution, rand point. We get like 10, 5, minus 7.5. So that was radius and xy position of the center of the circle. And then we got like the 3 points that we want to query, and the output would be null. And then 3 points on that circle with the radius 10, centered around 5 and minus 7.5. They go into a little more details on the syntax. Input is 2 lists, subroutines called, and their arguments. Solutions constructor has 3 arguments: the radius of the center, the y position, and x position of the center of the circle, and that rand point has no arguments. Arguments are always wrapped with a list, even if there aren't any, which is what we see here with those empty brackets. But later we're not going to spend too much time on the class architecture and rather straight only focus on the rejection sampling part of it. Now let's have a look at the theme, which is rejection sampling. And for today's explanation, we found a nice website presented by David B. Dahl, specifically only on rejection sampling, where he basically goes through the background, has a drawing on it, and defines the 4 steps necessary on the algorithm, which is key. And we're focusing on the algorithm. Nonetheless, it's a really good read, going through like the math behind it. specifically talking about that rejection sample seeks samples from the distribution having a density f. We do this by sampling uniformly over that region and marginalizing u by u, which might be difficult. And then he arrives at how to better do that. We can sample uniformly over the region B as follows. And then here he basically comes up with the approach that is then summarized. So what we do is we sample from the distribution having a certain density and sample u from a uniform distribution, but relative to the distribution having density f over these samples x at different degrees, depending on the value x. We can sample uniformly over the region A, which is xu, with fx greater than u and u smaller than fx, by sampling uniformly over B, and only keeping those values for which u is smaller than fx. Finally, upon marginalizing over u, we have x drawn from the distribution having density f. So that's where we basically rescale our distribution. And then in parts of steps, it's like sample xi from the distribution having density g, sample uy from the uniform distribution on 0 and e of xi, and then only if ui is smaller or equal than f of xi, except that one as a draw from the distribution. And we repeat this until we have collected the desired number of draws, which comes in handy when we want to collect certain rand 10 samples, or we want to collect a number of points on a circle. All things being equal, the algorithm is more efficient when that parameter alpha is close to 1. Again, that website is a really nice read to go through point by point and to understand the math behind it. It's short and concise as well, and basically gives us all the background in terms of the algorithmic steps that we now need to trace through and basically need to find and understand in the solutions, or in the variations of our theme when used to find a solution for those two problems. So with that in mind, let's have first a look at the sampling of the range 1 to 10 given a distribution of 1 to 7. And here we have also a submission where we nicely get like an explanation of it. Let's go through that one. So the first thought is to use reject sampling. After reject sampling, the number of outcomes would only be smaller than 7. Since we might reject some of the outcomes from 1 to 7. The intuition is to factorize the target, such that by sampling the two numbers from 0 to 1 and from 1 to 5 uniformly, we could use n1, 5 plus n2 to obtain the final sampling result. For sampling from 0 to 1, a naive approach is to reject 5 outcomes, so that only 2 outcomes remain. But too many rejections would make the function call grow. Instead, we could sample a number from 1 to 6 and determine if the number is even or odd. Now we only need to reject one outcome, namely 7, because it's the only odd outcome there. Finally, the expected function call would be 7 over 5 plus 7 over 6 equals 2.57. The expected function call could be thought as the expected value of a geometric distribution with the parameter p. In our case, it's p equals 5, 7, 6, 7 respectively. And since the expected value of a geometric distribution is 1 over p, we could easily calculate that result. So let's go to the implementation here. He's calling that function rand10, which calls rand with limit 5, plus, and here we do our modulo definition and see if it's an even or odd number. So rand with limit 6, and we only reject the 7, so to say. Rand with limit 6, modulo 2, if it's a 0, so if it's an even number, we shift all the values up to 5. And if it's an odd number, we don't shift them. That means we return something in the range from 1 to 5, plus either if it's even plus 5, if it's odd plus 0. And therefore we get like a sampling of 10, only given our range 1 through 7. And rand with limit, while true, we call rand7, and then we set our limit to be 6, which was the key thing for getting even or odd. If the randomized value is within that limit, we accept it. Otherwise, we'll continue. And that's why that computation of 2.57 comes from, saying that on average we need to call run 7 2.57 times within one runtime call. Bearing in mind that there are a couple of cases where we actually hit a 7 in this call, and there might be cases where we hit a 6 or 7 in this call, and in those times we actually have to reject it. Next up was the random point in a circle discussion. Easy to understand C++ solution using a rejection sampling with some really nice description on it. And again, there is some part on the data structure aspects of it, and just to make sure that everything's initialized correctly, which we assume is correct here by using the constructor. And we, however, want to focus on random point generation. So he uses random point generation here and then rescales it to the range of that maximum rand in order to get a range from 0 to 1. He scales it then from 0 to 2 and then subtracts 1 to basically get in the range from -1 to 1 and multiplies that with the radius. So now we get like, if you imagine your current center of the circle still being at the origin 0, 0, you might get a radius from, you have your radius, then you get from 0 to r, which is the radius, and from 0 to -r. That's your x1. And then your y1 has the same thing, the range from -1 to 1, multiplied by the radius. And what he ends up doing here is basically only to check if you are, so if you're doing the Euclidean distance from the origin of your randomly sampled point, if that Euclidean distance is within the circle, meaning if x1 squared plus y1 squared is smaller or equal the radius squared. If it's equal the radius squared, then you're exactly on the circle. If it's smaller the radius squared, then you're within the circle. Only in those two situations you will continue to go in here and actually return your pair of values. If that is not the case, you will continue to sample. That's where our while true loop comes in, that we have already encountered in the other example. So we continue to sample, and we reject when our sample is outside the range that we want to return in from. And that's basically the whole idea of using the rejection sampling here. Sample, loop and loop and loop, and only when you're within the range, continue to work with the sample values. And here, when we are in that range, the final step that we actually need to do is shift our circle from the origin to the specified center location, which is, just some constant addition to it. I think it's just to like motivate it more geometrically, but it doesn't have too much of an effect. The key thing is just we sample around the origin, we scale it in the correct range, and then we reject when we are outside our desired range. And that's all to it. That's all to it for the theme rejection sampling and our two variations that we saw. One variation to sample a distribution over 0 to 10, using only a distribution from 0 to 7, and here to sample a distribution on or within a circle.